In this lecture, we'll look at some very basic signal operations: addition, subtraction, and multiplication of signals. Now, this material is rather elementary, so we'll introduce the material through some rather silly examples in order to keep things interesting. We'll start off with adding signals, and so we ask the question, how do you add signals? We need to specify exactly what we mean by the addition of signals. To illustrate signal addition, we'll talk about how to find the position of the barnstormer Fearless Farnsworth above the ground from two other signals. And yes, that's his real name. So here we're adding two signals that are specified over independent variable time, x of t and w of t. We're adding them together to produce another signal, y of t. What do we mean when we say y of t is x of t plus w of t? How do we find y of t from the other two signals? This isn't hard at all. All we need to do is add the signal values at each and every time. So let's find the position of Fearless Farnsworth above the ground, y of t, from two other signals. And the two other signals are going to be x of t, the plane's altitude above the ground, and w of t, the height of Fearless Farnsworth above the wing. Now, that w of t is going to be measured positive in the upward direction. So as shown here, since Fearless Farnsworth is below the wing, w of t will be negative. So if we add the plane's altitude at any given time to the height of the man above the wing at any given time, we'll find the man's altitude at that time. It's just simple addition. So here's how we can represent this relationship in a form called a block diagram. We show the signal x of t going into a junction where it's summed with the signal w of t to produce the signal y of t. You see the two plus signs next to the arrowheads on x of t and w of t. This indicates that both signals are being added positively together to produce y of t. We'll use this type of diagram extensively throughout the course, so you should be comfortable with it. All it does is represent the equation at the top of the page. Y of t is equal to x of t plus w of t. Now, to give you a better understanding of this addition process, we'll specify some example x of t and w of t signals. X of t, the height of the plane above ground, will start off at 15 feet, and then after a period of time, it will increase at a rate of 5 feet per second until it reaches 25 feet altitude. The signal w of t represents the height of Fearless Farnsworth above the wing. This signal will start off at 0 and then decrease at 5 feet per second until the height is minus 10 feet. So at that point, Fearless Farnsworth is 10 feet below the wing. So here we see these two signals, x of t and w of t, x of t being the height of the airplane above the ground, and w of t being the height of Fearless Farnsworth above the wing. And we see their summation, y of t, which is the height of Fearless Farnsworth above the ground. So we've added these two signals together at each and every time in order to form y of t. This addition is really rather trivial, but I want to make sure you understand it, so let's look at it in a little more detail. So we'll compute the value of y of t by adding together the values of x of t and w of t at each time. So at time 0, x is 15 and w is 0, and adding them together we find that y is 15. We'll now look at another time. So let's look at 1 second. We'll find the value of x at 1 second, and that is still 15. And the value of w at 1 second, that's still 0. We add them together, we find y is 15. We'll now go to 2 seconds and do the computation again. So at 2 seconds, the value of x is 15. The value of w is minus 5. And so the value of y is 10. Now let's go to 3 seconds. The value of x is 20. The value of w is minus 10. So the value of y is again 10. And now at 4 seconds, the value of x is 25. The value of w is minus 10. And so the value of y at 4 seconds is 15. And now we'll go to this later time here. X is 25, w is minus 10, and so at that time it's going to be 15 as well. So something else I'd like to point out now is that between 2 and 3 seconds, x is increasing at a rate of plus 5 feet per second, while w is decreasing at a rate of minus 5 feet per second. So during that time, y is steady. It's neither increasing or decreasing. So I think you'll agree now that the addition of signals is a pretty easy task. What about subtraction? Well, obviously subtraction is really not that different from addition. All we have to do is just subtract the signal values at each and every time. So let's suppose we form new signal y of t by subtracting w of t from x of t. So we write y of t is x of t minus w of t. We can represent this in the form of a diagram as shown here at the bottom of the page. We show signals x of t on the left and w of t coming from below, and we put a plus sign next to x of t's arrow and a minus sign next to w of t's. And then coming out of that junction is y. So that symbol there indicates that y is x minus w. So now let's look at multiplying a signal by a constant. So we write in equation form y of t is k times x of t. And what this means is we take the value of x at each and every time and we multiply it by the number k. So at each and every time, y of t is k times bigger than the input signal x of t is at that time. So for example, let's look at x at 5 seconds. It has a value of 2. And let's suppose that k is equal to 3. So the output is going to be 3 times bigger than the input. So since x is equal to 2 at time t equals 5 seconds, y will be equal to 6 at that time. If you're thinking to yourself, wow, this stuff is really easy, you're right. We're not doing the hard material in this course right now. We're just learning some of the basics. I don't want anybody to be left behind when we talk about something being k times bigger. You'll note that the constant k relates the input signal x to the output signal y. And since this is a relationship between an input and an output signal, then we can think of the constant k as a system. It's a very simple system, but recall a system is something that takes an input signal and produces an output signal. An important part of the terminology of this course is the idea of gain. Gain is the amount of amplification that's provided by a system. So in this case, the gain of this system is the constant k. For more complex systems, the gain will depend upon the input signal. To illustrate this idea of this relationship between an input and an output, the output being a constant times the input, I want to do an example problem related to an extra credit assignment which you can do. If you survive being shot out of a cannon, I will give you 5 points on your first test. Trust me, this will be easier than some of the multiple choice problems. So the example problem is the dynamics of the human cannonball. What is the relationship between the input, the force F of t, and the output, the acceleration of the human cannonball, A of t? Of course, this relationship is A of t equals 1 over m F of t. So 1 over m is a constant relating the input F of t to the acceleration A of t. And we can show that in a block diagram, as in the figure at the bottom. F of t is the input going into the block, A of t is the output coming out, and 1 over m is the constant relating the two signals. So multiplying a signal by a constant is really quite easy. How about multiplying a signal by another signal? For this example of multiplying a signal by a signal, we'll bring out a story about Thomas Jefferson. Now, this story about Thomas Jefferson and the founding of the University of Virginia is little known, and it's little known because, well, I just made it up. So here's the story. Thomas Jefferson was very interested in the economic development of the Charlottesville-Albemarle region. That was really his prime goal in founding the University of Virginia. So why did he found the university? He wanted a world-class tourist attraction to bring tourists all over to Charlottesville. And he hatched a devious plot for this purpose. He would attract the best students from all over the world and have them live close to the rotunda. Then, one day, the active volcano that was hidden beneath the rotunda would explode, covering the students with ash and preserving their bodies in a grotesque display which tourists from all over the world would come and see. Fortunately for the students, but unfortunately for Jefferson, the volcano has remained dormant all these years. So here's the problem we're going to work on. We're going to determine the ash flow rate from the volcano at the rotunda. The ash flow rate is a signal, and to find it, we'll multiply two other signals. One is the ash density inside of the hot gases being released from the volcano. The other is the volumetric flow rate of the hot gases. So the ash flow rate we might measure in kilograms per minute, and then we can find that by first finding the volumetric flow rate. I'll call that signal V of t, and that might have units, say, of cubic meters per minute. And then I also need, of course, the density. The ash density I might measure in, say, kilograms per meter cubed, and that we'll call d of t. And so then I find the ash flow rate as the multiplication of V of t and d of t. I simply multiply the signals to find the ash flow rate. I do that at each and every time. So let's do a brief example here to show Jefferson how to do this multiplication. So let's suppose we have a volumetric flow rate which steps up at time 0 and then levels off and then goes down at about 3 hours, and then is 0 after 4 hours. And then we have a density which starts off very low, and then the ash starts to pick up. At 2 hours it gets to a maximum and then holds constant until the volcano has stopped erupting. What does the ash flow rate, F of t, look like? Well, this is easy to compute. All we need to do is to take the volume signal and multiply it by the density signal. And that will produce a flow rate as I'm drawing down here at the bottom. It starts off at 0 and stays 0 until 1 hour, then ramps up until 2 hours, holds constant for a while, and then it decreases again, stopping at 4 hours. And this is achieved simply by taking the values of V and D at each time, as I'm showing in the circles, and multiplying them together to get the values in the F of t graph. So it's just like adding, except it's multiplying. We just need to multiply the signal values at each and every time to find the new signal. As I'm sure you can tell, this material of adding, subtracting, and multiplying signals is all really elementary, and that's good. It's a good way to start off the class. We're going to be doing some much more complicated operations upon signals, and so this material will get more difficult, but I want to make sure that you have these basics down and are confused by any of the notation.